Okay, hello. I must apologize for the probably poor audio quality of this video. This is I'm gonna in this video explain a few ideas. Having no, I'm gonna just explain some work I did in about the start of 2021 with having to do with calculus and discontinuous calculus in particular. Um, uh, eh, right, so Eric Weinstein had this idea. I heard this idea by Eric or Weinstein that, uh, what day to pick where everybody could just take off their masks and whatever. There is no better day than April Fools. So I decided, to just upload the thing I wrote to the article I wrote, upload it online on April 1st, and this video online on April 1st. Though as of recording, it is March 29th, so April 1st is coming in 3 days. I started writing this article exactly 2 weeks ago, on March 15th. Writing up in later, but again, the work I did most of this work in about 2 weeks, in the start of 2021, or closer to the start at least. And the article, I don't think it's too good. So this is gonna be some of this video is gonna be reading the article, some of it is commentary or maybe elaborating on it, uh, especially on ordered aggregates. I hope to elaborate on that, what exactly I mean by it. Right, so the beginnings of discontinuous calculus by me. Uh, it's yeah, it's gonna be uploaded and online, released in 2021, the 1st of April. Right, so here's a note saying it's, I'm only one person, bad grammar, bad writing, whatever. Yeah, it is bad writing, but overview. I believe I have found a way to differentiate what have been known as undifferentiable functions, and to do this, I have developed an idea of aggregates, among a few other things, limits and epsilon proofs, which is basically my way of doing limits, which isn't too important. And I have some unresolved further queries into this topic. In particular, I have this intuitive idea of an ordered aggregate, which I haven't formalized or made rigorous, but I think it could probably help a lot in proving this thing. So, by the way, first I'm gonna talk about infinity, then infinity and limits, and only then about aggregates. So here's a bunch of stuff about aggregates, and then I'm gonna be doing aggregates, and only then how to differentiate these seemingly undifferentiable functions, but that starts at infinity and then limits. Okay, here everything's loading now. So infinity, the defining characteristic of infinity is that infinity is bigger than any real number. So if you give me any real number not too small, then of course there's the question, is infinity a real number? Which according to my definition, but it's a weird question. Honestly, there's probably some problem. I expect that there is some problem into exactly, actually no, there are problems into exactly what are real numbers. um Real numbers I don't think are very well defined, but that's not this is what's important right now. And then the limit of a function is the evaluation of the function at infinity, written as lambda of n. um you might be thinking, oh wait, no, that's limits, what are you talking about? No, no. uh, because I define limits in terms of limit, so that doesn't really work. So basically, with this characteristic, we can prove some pretty basic things which are usually taken for granted as far as I've seen, but again, I don't know that much. So actually, this proof is wrong. Well, a limit is an evaluation of a function at infinity. So let's take a function f of x equals x over x. So for all points, well, except 0, but we can ignore 0 for now. This is gonna be like bigger. No, this is gonna be just 1. So, and if you just pick any number a bigger than 0, right? So for all a bigger than 0, if you have some number b, right? So for all numbers b bigger than a, that would imply that f of a equals 1, obviously f of equals 1. That would imply that for any number like bigger than a, I mean b, f of b equals 1. And infinity is bigger than a, so the f of infinity, you could write it like this, equals 1. But usually there's some things about writing things, because sometimes you can write infinity like 2 to the infinity equals 0, but sometimes you can't write infinity, so you're like, this like doesn't equal 1. Well, it's semi-equivalent to 1, so it kind of is equal actually, but that's for later. That's when we come to aggregates. I can explain that. So for some expressions you can use infinity and it'll work. For some expressions you can take the limit as n of, let's say, 2n over 2. No, 2n over 2n over n. Well, that's just 2, right? So we can take the limit of a particular function at infinity, but sometimes we can't just there's a distinction in some expressions between, you can't just write infinity, you have to have extra information about its context, right? So here we could write f of infinity equals 1, or we could write lam n of f of n equals 1, and that's the same thing. So that's basically limits and infinity. Here I like this proof a bit, so quite a bit. Like if basically like 1/2 to the infinity, like infinity is bigger than 1, and like 1 2 over n, 1 over 2 to the n is not bigger. Wait, I have to it's not smaller than 0 for n bigger than 1, and infinity is bigger than 1. But also 2 to the n 1 over 2 to the n, 1 to the n and 2 to the n. Well, 1 to the n will be bigger than 0, and 2 to the n will be bigger than 0 if n is itself bigger than 0, meaning it's not a negative number, so it can't be bigger than 0. So 2 to the infinity, really, 2 to the n can't be bigger than 0. So it can be smaller, it can't be bigger, it's exactly 0. So 1 over 2 to the infinity equals 0. Alright, you can write this exactly, and for this expression we don't even need limits because there are no ambiguities. Like if you take the lim of this function f of x, and f of x is just like 1 over 2 to the x. This is, again, lim n of n, it's equal to the lim n f of 2n plus 1, or whatever you want. Sorry, that's not very legible, but you heard me say it, so. Okay, so the next part is infinity and the limits. A limit, I'm debating in my head, should I explain this very detailed and rigorously, or should I not do that? I'm thinking about it in my head, okay, infinity and limits. Right, so I'm debating, and I'm really not sure if I should explain it very rigorously or not, because I don't think I've made a mistake in this proof, but not in this proof, in this definition. Infinity and limits. A limit as a function tends to a point from a direction is the function infinitely close to the point from the given direction. Right, so this is, I'm defining the directional derivative. Okay, so I'm just gonna given a function, a point it tends to on the input space, right? And what we want to know is the limit as it tends to on the output space, like L. So what we want is a series of, basically, I'm gonna do the limit from above, and then I can just generalize it. So the limit from above, right? So you have some point which is c plus epsilon 1, and then we have some point that's in between these two. It has to be in between these two in such a way that on the output space the function of c plus epsilon 2, the function of it is smaller or at the very least equal to this one, the term that came before it. And what we want is that they get closer, but we don't want them to go below c at any point, below c, not c. So c, I'm pronouncing it weirdly. I got a bit stressed. It's not c. It sounds Chinese or something. I don't know, Asian maybe in Africa. I mean, Africa is very phonologically diverse, but right. So we have this point C, and it's big. So all this C plus epsilon 3 is basically they just never go below it. whatever these series of points is. Actually I should have started with c plus epsilon, oh, c plus epsilon 0 less than c plus epsilon. For some reason I'm writing infinity instead of 0. Okay, right, so we shall start yeah, c plus epsilon 0. So these numbers are getting closer, but then we can just isolate the epsilon plus the epsilon whatever. So 0 is less than dot dot dot, you know, epsilon 3 less than epsilon 2, so on. Basically epsilon n is less than epsilon n plus 1. Oh, and all of these epsilons are bigger than 0. That's the gist of it. And their functions have to be getting at least closer or equivalent, because like if you imagine a function like this with a plateau here, let's say we're getting to this point, well on this point in the output space, on the input space, we're going like this, right? So you can sort of come closer, but at this point nothing changes, right? But perhaps if we were traveling onto a point here, nothing should change from our initial point, but if you are traveling further, eventually you'll have to get infinitely close on the x-axis, right? So if it's not on a plateau like this, then it will eventually go down like this, right? But for most functions, you know, there are no plateaus, there are minimas and maximas and whatever, but these points all get infinitely close. So c plus epsilon infinity equals c, right? And what the limit is f of c plus epsilon infinity, which might equal f of c. Of course, if the limit equals the function of the point at every point, well, that means it's continuous. But well, for continuous functions this is true, but what are continuous functions? Well, they're just functions that fulfill that condition, so it would be circular reasoning. So I'm just gonna say, you know, so the question is, what is f of c plus infinity? And what we want is that we want to somehow describe so the sequence of numbers. It would be preferably described by a function, where if you take the function of g of epsilon 0, which is the initial input, it would get closer to c, right? So this would equal epsilon 1. And then if you take the function of epsilon 1, it would get closer to c again. So this would be c, this would be epsilon 2, right? And g of epsilon 2 equals this, and so on and so forth. So basically g of epsilon 1, well, that's just g of g, again, g is just some function that fulfills the requirements of epsilon 0, right? So all of these series of numbers can be just described by g to the n g's of epsilon 0 equals epsilon n. Right, so we have basically these two rules, which again describe a sequence of numbers getting closer to c, and then we'll take the function c, and that's the limit. Of course. So what else do I need? Right, so and it's getting closer, so perhaps you want to describe it getting closer. So f of c plus epsilon 0, I'll just say that's f0. This is f1, f2. Right, so oh, perhaps I should put it here. Fn equals the function. Actually, Fn equals f of c plus epsilon n. I accidentally wrote Fn equals f of epsilon n, but Fn should be Fn equals f of c plus epsilon n. Of epsilon n, which I've already described. By the way, this g to the n of epsilon 0, it's not, this thing to the power of n. It's like g to the 2 of n equals g of n, right? That's the notation I'm choosing to use. Right, so just for no confusion, I'm pointing that out. Sure, and if you look at these f's, they get closer to L, and L will equal f infinity. Right, so we have some points, c plus epsilon 0, but, well, what is c plus epsilon 0? Well, c plus epsilon 0 is just any number you choose that, traditionally it's used that for all epsilons. Epsilon 0 equals the initial, distance from c you choose. So epsilon is, right, so that's just, again, some notation. So epsilon, again, traditionally it's used that if for all epsilon this and this and this happens, then the limit is this. But it's when working with discontinuous calculus, you can have like functions which are have chunks of continuity, and then have chunks of maybe discontinuity or whatever. They have two like half of a function is continuous here, half of a function is continuous here, but right here they don't connect. So that's why you can't choose just any epsilon. You just so epsilon is just, so epsilon has to be bigger than 0, but it has to be smaller than some number eta, and I'll say it just has to be smaller than eta, and eta is just some number bigger than the absolute value of c, right? So if you choose a number bigger than c, then you can get closer to it. I think, actually I thought about it, I think I'm not, wait, does this definition work or does it? No, it has to be for okay, well, this condition, I think I'm not gonna rewrite the article, and I'm just gonna leave a bunch of these mistakes in there. Okay, just basically epsilon is bigger than 0, but okay, let's say this is f of x, and then here it goes all wild. Right, so if you want to take the limit to c, you just have to choose some epsilon within the distance of continuity. So epsilon would be, okay, epsilon is bigger than 0 but smaller than the border of continuity. What? Now I need an idea of continuity to describe limits. And of course, continuity is described in terms of limits. Okay, well, it's possible to describe functions that are continuous everywhere, and for that you wouldn't need limits. For that you can just choose any epsilon. So if a function is continuous everywhere, then you can choose any epsilon. But for locally continuous functions, you need to choose an epsilon that is within that range of continuity, which I haven't described rigorously, and I'm not going to, but that's the intuition here. Right, so if you choose like any epsilon such that, again, epsilon is bigger than 0 is bigger than epsilon is bigger than some eta. Actually, yeah. Oh no, this definition works. Yeah, this definition works because eta is some number. You don't have to have all numbers bigger than c. So if eta is here in the discontinuous part, well, then it won't. Then the limit won't work. So then it doesn't work. But if there is a limit that works, well, you can just find it by not being in this range. So yes, this definition does work for eta bigger than the absolute value of c. Eta bigger than absolute value of c. If for any epsilon that fulfills these conditions, that implies there is some function g of epsilon such that 0 is less than epsilon n is less than epsilon n minus 1, such that the distance from the limit on the output space is of f of n, right? So if you take a step and you take a step back, you have to get either the same, like if you take a step forward, I'm basically just formally saying like, yeah, the f of n, if you take a step forward, you're either at the same point, you're getting closer or stagnant on the output space. F of x is less than or equal the absolute value of L minus f of n minus 1. So this is just the positive limit, the limit from the plus direction. But of course, what about limits from other directions? Oh, so if this condition is fulfilled, then the limit as x tends to some point c from the positive direction or from 1, which I'll explain later, from 1 or positive direction something of f of x equals f of c plus, well, I better write it like this, lam of n of f of c plus epsilon n. Right, so if this condition is fulfilled, the limit equals this. Right, so if you prove this condition, which is cumbersome, then you just have this and then you just solve this limit problem. And that's why limits aren't necessarily the same. Well, you can take a limit as x tends to infinity. Actually, I've just realized the lemma, right? Because in the article, at the current point, I might rewrite some of it. There is only one lemma. There should be another lemma, limit as x tends to infinity or minus infinity from a direction of f of x, this equals the limit n of the limit as x tends to n from a direction of f of x. Actually, this is a lemma that I didn't think about, so I didn't mention it in the article, of course. But how do we generalize this thing to what if you want to come from any direction? What if you want to come from the minus direction? What if you want to come in from the complex plane? That's a bit more difficult. But not really that much, because if you add, again, all of these epsilons are bigger than 0. They're all positive. So if you add them, you go from above, and then again, then you just get closer, right? So if you subtract them, you go from this side. If you want to go from the complex one, you multiply them by I, right? So you don't need to do much. All you need to do is say that fn equals, what do I need to change here? Yeah, fn equals f of c plus the direction you want to come in, d, and it's important that d does not equal 0, because, well, if you add 0, you're already at that point. So what direction are you coming from? Though actually I just thought of it, the limit from 0 might just be the limit from all directions, which would probably simplify some things, maybe make some things harder. I don't know. Probably a wrong idea, probably stupid, but again, just d doesn't equal 0. It's whatever complex number you want, and just take this and fn here. So in here, right, we don't need to change anything. Again, all the epsilons are positive, and then we just multiply them by some constant to like change their direction. So if you could imagine, like, the epsilons are a magnitude, and then when we multiply by d, that's basically gonna be the direction of a vector, if we imagine it like that. And here, so if this new refined A, if this condition is fulfilled, then this is true, right? So now we can just take limits, and then, well, this has gotten I'm just on the third page, and I've spent half an hour, so I'm not going to go through the example I use. I'm not going to go through, because I used here's the example, like the limit as x tends to 0 of a times x square. What? Oh, here I've made the limit a x squared over x, and then I accidentally added an a here. Well, actually, I wanted to do the proof with an a here, but then I accidentally forgot it. So okay, I'll just remove this a in the final article. So aggregates. Now this gets into the like juicy meaty bit, and then probably the most problematic bit, because this is mostly what the article is about. Aggregates. Most simply, an aggregate is a multiplicity of objects. But what does that exactly mean? Well, that's the yeah, that's the part of me. Okay. So Plus or minus signs have always confused me because I don't really understand like what is it exactly supposed to mean, like how can it be like for plus or minus, because again it's like in like the basic algebra, like a plus or minus signs appears in the quadratic equation, right? So it's useful stuff and it's important stuff, but like it didn't fully make sense to me until a few months ago. uh, which I just kind of had forgotten about it, and then I remembered it. So the most simple example would probably be the solution to the equation what is x squared equals 3. Did I seriously write x squared equals 3? Holy, oh, that is such a dumb mistake. That should be 9. What am I doing? Wow, that's so stupid. Right, so x squared equals 9. I can't believe I actually wrote x squared equals 3. So the solution is like plus or minus 3, right? So it's often expressed, I've seen it often expressed as a set, like this. But then like again in the quadratic equation it's minus b the square root of blah 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 blah, like plus or minus. Yeah, I might draw a number line, right? So here's 3, here's minus 3. So plus or minus 3 is these points at once. Oh, now the minus 3 looks little. So it's these points in a certain way at once, but you can like do things you can't do with sets with these plus or minuses. So 5 plus or minus 3, so that's either 5 plus 3, that's either 5 minus 3, which is 2, or that's 5 plus 3, which is like 8. This isn't very much to scale, is it? But this isn't to scale at all, to be honest. But like, so plus or minus 3, like plus or minus 3 were in a certain sense these points at once. 5 plus or minus 3 is like 2 and 8 at the same time. And we can describe more than just 2 points. We could 2 points at once. We could describe 4 by just adding another number. Not 4. This describes. Wait, how many numbers does this describe? This describes 4 points. And now 6 points. Well, maybe. Actually, I'm not entirely sure. Because again, it could it could describe a few numbers that are not unique. Well, again, this depending on what numbers you choose. If you choose some of the pluses and some of the minuses, they could output the same number. But so a 5 plus or minus 3, that's 2 numbers. But if you add the like again, it could describe this like if you add another plus, that could describe 4 numbers, or it could describe only 3 numbers. And I think I found I found a formula to describe like almost any numbers you want that are possible, but some are impossible. I forgot the formula. It's not very useful, especially when we have aggregate. So the aggregate is like there are certain things you just won't be able to write with these plus or minuses, and these plus or minuses obviously are not sets. Like you can't take this, can't take the set plus or minus 3 and just like add 5 to it. Like that doesn't make sense. It's undefined. Addition is not defined for sets. Like conjunction is, but addition no. So the aggregate, no, so the square root of 3 equals 9. The right, so x equals the aggregate of 3 and negative 3. So those are both solutions, right? And now, like, if you take this, oh, right, so, and, right, so, yeah, we have this aggregate, and then with this aggregate, we should be able, like, to do the things we usually want to do with plus or minus 3. So if we wanted to square x, well, that's obviously just 9, right? So if we square this aggregate, well, it equals 3 squared and minus 3 squared, right? Which 3 squared equals 9, this equals 9, so this equals the aggregate of 9 and 9. And like 9 and 9 at the same time, well, that's just the same thing as 9 by itself, right? So we can just reduce it. Or we could do this. We could take the aggregate, 3 minus 3, you could add 5 to it, which would equal 8 and 2, right? The aggregate of 8 and 2. And this doesn't reduce nicely, obviously, this doesn't reduce nicely, but it's still valid. And here there's a certain problem, which actually at the moment right now I haven't written at the very end as for the unsolved questions, but it is one of the unsolved questions. Like, because there is a certain sense, like, you can multiply. There's a distinction between a function of an aggregate's elements and a function of the aggregate. In a certain sense, there's a distinction which I have not made. Which I think I'll talk a bit more about aggregates, and then I'll say the unsolved thing. So right now a little beyond aggregates, double torus notation. Basically, double torus notation works just like sigma notation, except it enumerates elements of basically a thing which needs to enumerate elements, which could be anything. It could be a set, it could be an aggregate, it could be a vector, it could be anything really that is composed of elements, right? So if we have like this sigma notation, xi, this is just the sum x1 plus x2. But if we have like the set double torus x equals 1 to 2 of xi, well, this is an enumeration of the elements of that set, so this is just equivalent to 1, the set of x1 and the set and x2. That's it. Or even an aggregate. You could do the same thing with an aggregate, though notationally aggregates and sets are quite similar, where all I need to do is just like, actually I just need to take away that, and here I can just write the aggregate as this. And of course, if these two x's are equivalent, then you can reduce it to a particular value. So the Don and also besides double torus notation, the Don function is just it's like the the Don function is like the cardinality of sets. So if we had the set x1 and x2, the cardinality of it equals 2. If we had the aggregate of x1 and x2, the Don function of the aggregate equals 2. If and only if x1 does not equal x2, because in that case it would reduce to a particular value, and then the Don function would be 1. So the Don function of an aggregate is just a measure of how many elements it has. And of course, if you pick just any particular thing that isn't an aggregate, like let's say we have I don't know, Russell's set. Actually, shit, that doesn't exist. Whatever set you want, I'll just say 1. Well, that the set of 1 equals the aggregate of the set of 1, which notation a bit wacky, but the Don function is 1, right? And this is perhaps when you have the equation x squared equals 9, you want a solution with a Don function of 1, right? So you could say that now it's a system of equations, x squared equals 9, and the Don function of x equals 1. So now it can be equal to the aggregate of 3 and -3 because it has a Don function of 2. So in this case it would be like, well, you could write it as the answer to this is in the set 3 and -3, or you could say, which is basically you could say more generally perhaps that it's semi-equivalent to 3 and -3, which basically, like all the things you can do with sets, you set operators you can just do with aggregates. So if you have an aggregate with multiple elements, if you have an aggregate and you want to put the aggregate's elements together with another aggregate, you can just do that. I'll say there's an aggregate 1 and you want to aggregate conjoin it. This isn't a set operator, because I have very original notation for this. I just take the set symbol for conjunction and put a little dash on it. A2, this is the conjunction of the elements of these aggregates. Alright, so I've already said that aggregates like this, they simplify. Again, if an aggregate has multiple of the same values, you can just remove them like this. And an aggregate of aggregates, let's say it equals the aggregate of all the elements and sub-elements and sub-sub-elements, etc. I'm writing this very quickly because I'm getting really tired, but again, in the article I've written this. I've written this like formally, so here are the formal definitions. Here are all of the definitions highlighted right now. If you want to read them in more deeply, just pause the video. Here is basically all the things I've described. Also, I've already said about the double torus notation and the Don function. This symbol It's just you take the empty set. Oh, the empty set, and I just flipped it. This symbol just means undefined. So if something is undefined, I'll say it equals this, which might not be the. I'm not sure if it's the best choice to conflate equality and undefined. Maybe it'll backfire, but if I had this, a set plus a number, I'd just say it's undefined. Um, but again, it's very easy to write, so I just use it for that reason. Um, right. Oh yeah, I said something about semi-equality somewhere here. Semi-equality is basically means like if a sub-aggregate, like if you have a1, you could write that it's the uh, improper sub-aggregate, or that improper sub-aggregate of a1 and a2. But if you have just something like this, like if you have something like a relation like this, where it's a sub-aggregate of 1, you know that this includes this. But with semi-equality, one of them includes the other, but you don't really know which one. Which sometimes you just don't know which one, so that's why so that's what semi-equality means. Also, indeterminacy is really better understood using aggregates, because which you can infinity over infinity, like we and under oh of course, then you would have that any constant 1 by this would equal to 1 by a. Actually, this is kind of true. Yeah, you can just say a is an aggregate. So the Don function of a doesn't have to be 1. So this is actually kind of works accidentally, but and then you could just multiply by c2, and you equal c2 times a, and like if you pretend this is like 1, you just get that it's the aggregate of all these numbers, for all numbers that are basically, for all real numbers that are bigger than 0, that's the aggregate. And then if you have infinity minus infinity, well, it equals the aggregate of all real numbers in total. And 0 divided by 0 equals a time. Actually, it's not. Shit. Yeah, it's a times infinity, any real number times infinity. What is it? Shit, I don't think this is correct. Maybe. I am uncertain. Yeah, I think that's accurate. Whatever. You can have okay, the proper proof to this probably includes limits, and you can basically have infinitesimals with not limits, limits. Anyways, this thing equals over for all a in the complex numbers. So that's that for indeterminacy. So what comes next? I think there's a pretty good grasp of aggregates by now. Right, continuity and derivatives. So a derivative from multiple directions, which again we've only took derivatives from one direction. If you have a derivative from multiple directions, it just equals the aggregate from the limits from those directions, which is originally, this is the problem that I discovered. I prefer the word constructed, whatever. Developed the idea of aggregates for the first time, because like if at the point and around the point a function is continuous, then again these limits, as x tends to c from a direction 1, from a direction 2, these both equal, if these both equal the same thing. Right, so yeah, so if these limits again like are equivalent, then this will simplify. You get the value, right? So traditionally, if the limits from multiple directions are equivalent, the limits from both of those directions at once are again the same as any one of those limits, not the same as both, really. But with this definition, if the limits aren't equal, i.e. the function is discontinuous, you just get an aggregate like this, and then you can do. Basically, this is what allows calculus with discontinuous functions. So if this right, so that's limits, and of course it's getting quite late and I'm getting quite lazy, so I'm just not reading some of this. Here I highlighted the definition of the limit from multiple directions. Okay, and now with aggregates we can actually generalize the idea of continuity, because like if you have a function like just whatever scrambled whatever, right, like there's not really a sense of continuity, but like a function like this, like it has continuity, but a function like this, like it obviously has this sort of function obviously has something similar with this function. Like you might not be able to kind of put your finger on it, but like intuitively, like these kinds of functions, like if you have a function of multiple functions that are themselves continuous, like this intuitively to me seems to have a certain quality that a jumble of whatever doesn't, and that is n continuity, or n output. So an output continuous function is a function whose, well, of course, continuity from directions, right? So you could, on the real plane, you can have continuity from this direction and from this direction. On the on the real numbers, on the complex plane, you can have continuity from any direction. So continuity from any direction. Right, so here is the definition of of n output continuous functions, or n continuous for short. The thing is, like, some of the functions might have local intersections, in which case, like, in a sense they are globally two continuous, but there are there are some spots where they intersect, in which case they would be one continuous, which is one of the problems that I think ordered aggregates might solve. Um, uh, the the derivative from multiple actually this definition, yeah, I did define it under an interval. Yeah, continuity over an interval. Right, so the derivative of multiple directions, the directional derivative is again just this, right? So I just picked the here it's just the regular definition from a certain direction, so the plus derivative or the minus derivative, but again here is from any directions. And with limits, of course, if you have a limit, if you want to have a limit, not a derivative from multiple directions, of course you just take the limit from multiple directions, which is the aggregate of these things, the limits of these from directions. Right, so with this we can sort of differentiate what have been formerly known as undifferentiable functions. So the absolute value of x, it is differentiable for values not equal to 0, but you can't differentiate with respect to 0, because the derivative from one side is not equal to the derivative from the other. But with aggregates, it's not about that the derivatives aren't equal. It's just the aggregate of both of those unequal derivatives, unequal, not unequal, unequal. And here's just the so if we differentiate absolute value of x, you just get this. And if we differentiate this function again, we just get 0. So perhaps this can build some intuition. So the derivative over here in the plus direction makes sense. It's just the tangent line, which is this. The derivative here makes sense. But the derivative on this sharp point, well, from one direction is the tangent with this. From the other direction is the tangent with this. So it's just the aggregate of both of those. It's the aggregate of both of those. Kind of looks like a emoticon, but whatever. Right. So the function we get is when we differentiate right, is this function, and if we differentiate it again, well, on here it's 0, here it's 0, here it's 0 and 0, which is, well, here it's from this direction 0 and from this direction it's 0, so it's 0. Right, so the derivative of this, or the second derivative of blah 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 equals 0, which again is sort of the reason I took the first derivative of absolute value of x, because you can't differentiate it. I took the second derivative as foreshadowing, sort of, because 0, wait, if you integrate 0 you get c, right? And then if you integrate c again you get cx. But this isn't c. Well, what gives? Alright, so then basically I just give a definition of, oh, I forgot to mention one thing. Quick aside into limits. You might be thinking, oh, why do all epsilon whatever have to be rational, not natural numbers? They don't have to be. You can just define that 0 less than epsilon a less than epsilon b for a bigger than b, and just sort of replace everything here with that sort of a bigger than b, and then you can generalize to the rational numbers, not just the naturals, which I believe in some cases would be much more useful. So, but okay, we are advancing. Okay, different. Yeah, here again in very technical terms. Basically, oh, if we have a function that looks something like this. Okay, so basically what I quite formally describe is if we have a function looking something like this, where it's cut up into here's the point I1, I2, I3, and it's sort of cut up into intervals between these. What would the derivative be? Well, just looking here, well, I mean, it's pretty obvious locally because they're all locally continuous. Well, this one isn't locally differentiable, sharp point, but actually, what I'm gonna make these points much sharper. Right, so, but still, they're continuous. So what happens here is pretty obvious. But what happens at the side? Well, at the side, like even if the point isn't included, the derivative, no, like as it tends to the derivative from the minus side here, it tends to the derivative of this. And this is, n to, m plus 1, and this is m plus 2. And this is described by f of something or other. Oh no, this is described by fn of x, and this function is described by fn plus 1 of x, fn plus 2 of x, etc. So here, from this side, the limit becomes from this side as it tends to the derivative. The limit, it seems to be this, and it is this, and from this side, it is obviously this. So the derivative at here is gonna be the aggregate of both of those antiderivatives. Oh wait, we didn't write. Right, so the derivatives, like, so it doesn't matter whether the point is included or not. The limit is this all the same. The limit doesn't change, all the same. So here is something what the derivatives like approximately look like, very approximately. But I just drew them by eye and hand, obviously. Obviously, because look at them, right? But notice that at the borders, they're all the same. Though of course you could have a Don 2 continuous function, and again it works all the same. Just include this, and then I'll include this. Alright, then it works all the same. So you basically cut up the whole x line into these INs, and basically what you have to do is I1 equals minus infinity, and if you cut it up into and IN plus 1 equals plus infinity. Why not IN? Why not? Here I wrote IN, which is pretty bad. Like the most this shouldn't be n. I'll just change it to like eta instead of n, because then, okay, then this is clearer. So eta is probably smaller than n, except at the very top. Like, so there's a bottom limit I1 and there's some top limit in plus 1. Yn plus 1, why not just in? Well, here it looks like, oh, that's just trying to make things more difficult, but if formally it's just easier formally. So here's here's it. What is it? Here's the differentiation of partially continuous functions. That here, I mean, here I just declare those things that need to be true so again, if you want to read it, you can just like pause the video. Right. Oh, actually, yeah, I haven't defined the derivative of n continuous functions. Well, here's just the definition. The derivative of an aggregate of n continuous functions is the aggregate of the derivative of those functions. Yep. Indeterminacy of integrals. Yeah, that's finally indeterminacy of integrals. Well, integrals, everybody obviously knows that the integral of a function equals the antiderivative plus any constant, and you can just add any constant and it makes no difference. But if we can differentiate these sort of cut up functions, then when we, because again, I've already shown that 0 equals, well, it equals obviously equals the second derivative of x with respect to x, but it also equals the second derivative of the absolute value of x with respect to x, right? The second derivative. And the only difference is because they were cut up differently. So when we integrate, we need to cut up the whole real line. So for this, if we want to get from 0 to this, we just first we cut it like this, and then we basically, and we choose, when we integrate the integral of 0, well, that's 0 plus a constant or just a constant. So I cut up the function to be, here it can be a, here it's wait, here it's just this. Right, so I choose this point to be, this to be 1 and this to be minus 1. Actually, I'm not sure about the inclusion on the borders there. Can you? Yeah, you can basically choose to like include or not include points on the border, but for this example, I'm pretty sure it's necessary to choose that they are contained, because then we take another antiderivative. No. Oh, well, here's one problem. Yeah, here's a problem. Here's one of the big problems is that, like, if I have a function like this, I can't integrate it here because no differentiation, because if I do differentiate here at this like cutoff line, it would include this point here, but so yeah, so there is no integral for this kind of function, right? Yeah, with my current definition, which are probably wrong, and ordered aggregates might help. There's something that might help, but again, this is a problem which actually I've studied before things like this, and it is somewhat related to some other ideas I had that with like what I call infinity overflows, but that's a completely that's a different topic. So basically the integral, yeah, if we want to integrate it twice, we have to choose that these points are included, right? So we can choose to integrate it like this, by just adding the constants, because again the constant we add is arbitrary, but it does have a physical interpretation, like with having to do with acceleration and velocity. It's physically interpreted. The added constant is physically interpreted as the initial velocity when dealing with acceleration. But again, this is one of the questions: is how would these intervals of integration be interpreted physically? That's the question. Yeah, how would they be included physically, right? So here I choose these constants under these, and I choose the intervals arbitrarily, right? So again, before constants were arbitrary, but now these sort of how I cut up the function is also arbitrary, as long as I cut up the whole, everywhere is defined. As long as, well, there can be undefined points like this. If I had this, I could differentiate it to get 0, so that is a valid the integral. But so but now so the again, the arbitrary element in physics has been interpreted. Now there's another arbitrary element, which is the interval of integration. So but again, like, so here I1 would be minus infinity, I2 would be 0, and I3 would be plus infinity. Here I'm just gonna go I1 equals minus infinity, I2 equals plus infinity, and I'll choose the constant 1. And then if I integrate this again, I'll get x on this side and minus x on this side. And if I integrate this again, I just get here this. Oh, plus a constant, but again, I'm gonna ignore it. So yeah, there are intervals of integration, and of course I have it formally right here, and then I have this cheekily titled exercises left for the reader, which again I'm gonna add a few more, because again the integration, there is an integration problem. So first, what are ordered aggregates? I'm gonna get into, okay, one, I've mentioned how to physically interpret intervals of integration, and also look at this trick, which there is a valid way of integrating 0 to get sine of x. And again, I cheekily put in QED. Basically what you do is you just you just take a certain limit. So you have a function like this, and then you just cut it up into pieces, and then at every piece it equals the value of the whole interval of this equals the sine of it equal. Here's a point in, so its height for this interval above it equals sine of in, right? So you get, boop, 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 right? Well, that's not the sine function, but yeah, you get like this stuff. And then if you take the limit, a sort of the distance between these points gets small, or no, really not the limit. I took the, because it's easier to do, I took the limit as, again, something gets big, but again, but that doesn't really make a difference. And then again, if you integrate it, you get a sine wave. So I really doubt, like, I'd be incredibly surprised if there is a context in physics where there would be a valid, like, interpretation of intervals of integration that would have you get like integrate functions to get very bizarre functions. But the point I'm making here at the very end is that an integral of something, if you just choose the right intervals of integration and the right constants, it can be anything, really. Like, that's the point I'm making at the very end. But again, just okay, then also, yeah, I've mentioned the, here I need to add in a third one, I think, and something else about, like, again, integrating functions that have like gaps somewhere. Can you integrate those? Like, or basically, is there how do you make a derivative? Oh, you might be able to do it with it might be possible with limits. Like, how can you differentiate a function to get something like this, which again, with the current my current definitions is not possible. Oh, wait, I think yeah, there is some reflection going on there that the camera is picking up. Yeah, here again, I don't take the limit, I take the limit, as two things get big, and then just blah 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 sine of x. So what are ordered aggregates? I imagine aggregates, so here is really the biggest thing I didn't explain, but I think it's the most important to go forward. Ordered aggregates would be aggregates with order, and they wouldn't have reducibility in the same sense that normal aggregates have. So A and A equals A, but A, let's say position 1 and A position 2 would not equal just A. And again, there is a certain, like, functions of aggregates, sometimes they are, like, if I add to an aggregate, I add to all of the elements, but like, look at this. Like, if I square it, sure, that's the square of the things in it. Or is it? Because it could be the multiplication of these two aggregates, which is not exactly the same, it's almost the same, because then if you multiply this would equal the aggregate of A times A and B times A and B, which would equal a squared ab ba b squared, which equals a squared ab b squared, right? Which I've sort of swept this under the rug because I did plus or minus 3 squared equals 9, which it might not. It might equal the aggregate of 9 and 9. Oh, that's a bad example. No, it might be the aggregate of 9 and negative 9. So again, there is sort of, I haven't made a distinction of whether a function is really on the aggregate or on the elements of the aggregate. But so it might have to do that. Perhaps you could define a function, because whatever you do, you can't just have a function of aggregates or a function of the elements of aggregates, because, well, initially, of course, I assume that f of an aggregate, I'll just pick a generic AB aggregate, that just equals the aggregate of A, and the aggregate of the function of A and the aggregate of the function of muscle memory. And the aggregate of the f of A and the aggregate of f of B. Well, that's not necessarily true, because again, the aggregate operators, right? Because what you might want to do is you might again want to do conjoin the elements of different aggregates and something like that, and that would be if something like this, conjoin this CD, if that was actually thinking that would equal, this might be a bad example. This does work accidentally. This accidentally works, which of course this equals ACD equals BCD, which of course then you can just reduce this. I'll just forget this part for a while, and then you can just reduce this last part, and reorder. Okay, well, this is a bad example because it does work, but again, this example, right? This example, it might equal 9. It might equal the aggregate of 9 minus 9. Whether it's the function of the aggregates or the function of the elements of the aggregates. But with ordered aggregates, you don't need a distinction. Well, I think the distinction should also be made, but I think ordered aggregates probably have a better interpretation than something else, but intuitively, so again, if you have an ordered aggregate of 3, I'll just pick up example 3 with position 1 and minus 3 with position 2, and you square it. Well, it might be just the square of the elements, or it might be it could be just the P1 minus 3 P2 times this aggregate times this, which equals, you don't multiply everything with everything, you just multiply what goes in the spots, what goes in the right order. So that's 3 times 3 at position 1, and minus 3 times minus 3 at position 2, which of course equals 9 position 1, 9 position 2, which again, as I've already pointed out, is not the same thing. But what you might be also able to do, an idea I had, you could make temporary, like you could give some arbitrary, like you could have a function that takes in aggregates and gives them some arbitrary ordering, and then you could sort of work with the ordering, and then you could just sort of get the order somehow out of there, getting 9 equals 9. Alright, so that might be how you, maybe you have ordered aggregates, and then if you have some sort of temporary order enforcement, you could just sort of enforce it, do the stuff, take it away, and that's how that might be how you can differentiate between functions of aggregates and functions of elements of aggregates. Perhaps thought, and there are probably, I suspect that is a valid way, but there's also another way. There's probably multiple valid ways, but also one of the things I define the derivative from multiple. No, what do they do of the derivative? Wait, did they do something in now? Oh, the derivative. Yeah, I defined the derivative of f of x, g of x. If you want to differentiate that, what if we use the formula? And again, this is pretty slow to write, but if you can just think it in your, you can probably just think it in your head quicker. Oh, minus f of this and that all over h. Well, again, this thing does not equal this thing. Quite obviously, because again, you're gonna have 4 terms in there, and yeah, maybe it turns out some of them are equivalent, but again, generally speaking, they're not the same thing. Well, there are cases where they are, but generally they aren't. And I just sort of defined this, and I sort of swept it under the rug. But again, this, there is a definition of the derivative, and this doesn't really follow the definition. This is just arbitrarily enforced. And again, I think ordered aggregates, with ordered aggregates, you wouldn't be taking away this from this, right? You would only be taking this from that. So if you did this with ordered aggregates, this would work. This would, right? Or if, again, the distinction. Because again, if you sort of, because again, the way I'm inclined to view the derivative is as a differential operator. So I imagine this as a function of this, and then I just do the function of this, right? D over x. But if I think it more by its, actual definition, well, then it's not so. Yeah, then it becomes a different thing, right? So that's what I mean more by ordered aggregates. Yeah, I'm gonna need to. Again, I have 2 days left. I'm gonna need to rewrite the article. Yeah, I'm just gonna rewatch this, and correct where I found some mistakes, because I have proof checked this once, and I thought it was correct, but now I found a bunch of incorrect proofs. So yeah, but that's basically it for now, hopefully the sound wasn't too terrible, the audio quality. Um, yeah, that's like 2 weeks of what I worked on. Actually, like discovering this, inventing whichever one I pick, half of the people will hate me. So I'm gonna pick constructed, so that everybody hates me. Um, so again, this took uh, about 2 weeks to do, but to write it is apparently harder. Not what you mean apparently. Uh, Most people are probably like that. Maybe they aren't, but again, I think a sizable amount of people would probably be like me. Um, I don't know if you want. I don't know if anybody wants to. Again, I am nowhere in academia. I am not in academia. So if anybody wanted to get in contact with me, I know. Send a comment. I know. Send a Gmail. Send mail. Whatever. Um. Well, I don't know. Goodbye and good luck, and hopefully somebody isn't. Hopefully somebody is interested enough somewhere out there and sees this video and yeah becomes interested enough to perhaps go further. Uh, Goodbye and good luck.